In this example, we're going to look at how we can use technology to solve equations and inequalities graphically. So let g of x equal the quantity 100 minus 3x times the quantity 20 plus 5x. And let h of x equal 215x plus 500. Use graphing technology to determine the following. And we're looking for points of intersection. We want to solve g of x equal to h of x, and g of x greater than h of x, and g of x less than or equal to h of x. Okay, so I'm going to go to Desmos here, and I'm going to enter h of x equal to 100 minus 3x times the quantity 20 plus 5x. Okay, so I see a little bit of that graph. And then I'm going to hit enter, and I'm going to enter g of x equal to 215x plus 500. Okay, so those are the two functions given in the problem. And now I want to see their intersections, right? I know that if I FOILed h of x, it would be a quadratic, right? Which would have a parabolic shape. And then g of x is linear, right? And so if you're looking at setting a good window, even without foiling that first one, I'm looking at the second one and saying, well, the y-intercept is 500, right? So in order to see some of the key features of that graph, we're going to have to do a little adjusting here, right? Okay, so we can zoom out. We see in that window we start to see something, right? And we notice it's going to take us a while to get a good handle on where the vertex is of that. And I almost like having a little bit more separation in the axes. One thing I can do is along the y-axis, I can just squeeze with my fingers, and that'll change the scale along the y-axis a lot. Okay, so then I see the purple graph there is the line. I see it crossing there at y equal 500. Now I see an intersection point down below here, so I want to keep that point, and I assume it's going to intersect somewhere up here as well. So I'm just going to keep squeezing here. Ah, there it is. Okay. Okay, so with some proper adjustment to this, going back and forth, because we're solving equations in this, and the first question that we were asked is, what are the intersection points? So it'll give me a lot of the key features of the graph. It's this one I want, though, that intersection between the two graphs, and it intersects at two places, right? The line will cross in two places. It looks like it's also giving me intercepts here. If I want them. We're a little less concerned about that right now. Mainly we just want the intercepts because we're wanting to solve h of x equal to g of x, right? Okay, so now that we have that graph, we can talk about the points of intersection. So the 2 points of intersection that we have are -5, -575, and 20, 4,800, right? All right. So then when it says solve g of x equal to h of x, okay, if we were to put these two functions equal to one another, right? The 100 minus 3x quantity times the quantity 20 plus 5x equal to 215x plus 500. We would be solving an equation for x, right? And we would say x equals some value when we were done, or values, right? So the values of x that make those two functions true are the values of x where the two functions intersect. Does that make sense? I hope it does. So the values of x where both g of x and h of x would carry the same y value are at those 2 points of intersection that we just listed, right? So they carry the y value of -575. Both of them carry that value when x is equal to -5, and both of them carry a y value of 4,800 when x is equal to 20, right? Okay, so just that concept of what does that mean when we're solving an equation. So if it says solve g of x equal to h of x, We know that when x is equal to -5 and also when x is equal to 20, those two functions are identical, right? Their y values are identical. So the solution set, we write it in set brackets, would be -5 and 20, right? So essentially, the solution of one function equal to another is equivalent to the x values of the intersection points, okay? All right, now solve g of x greater than h of x. First of all, we should make sure that we define these things, right? So g of x is the orange graph there, the parabola, right? And h of x is the line, right? The purple one. Okay, so when we're saying where is g of x greater than h of x, we're saying where does the graph of g lie above the graph of h? For what values of x does that happen? So I'm going to shade the part of g of x that lies above h of x. Okay, so when I say lies above, where are the y values on the orange graph of the g of x there greater than the y values of h of x, the purple line? Okay, so where that happens is from between the intersection points, right? Yeah, those are sort of the hub, and so we're saying where is the parabola above the line, right? And it's for this part that I'm shading in green. Yeah. Okay. So when you state the solution set, what you're stating is the domain of that piece, right? Essentially that we just shaded in green. So the domain of that is going to be from -5 to 20, right? So we're stating the x values where that's true. For x values between -5 and 20, the function g lies above or is greater than the function h. Okay, now when it says solve g of x less than or equal to h of x, okay, now we're saying where does g of x lie below h of x? So where does the orange graph lie below the purple one? All right, so where does that happen? And it's less than or equal to, right? So I have solid dots here. Down below here, you can barely see that. And then from the intersection point out this way, right? So the part that I'm shading in red here, there are two intervals, right? Where that happens. Okay, and we have to define the x values that make that true. So essentially, if you just state the domain of the piece that we just shaded in red, those are the x values where g of x is less than or equal to h of x. Okay, so where is that? It's going to be -infinity up to -5, and I'm going to include -5 because we have g of x less than or equal to h of x, in union with 20, closed bracket, right, to positive infinity, right? We don't have arrows on there, but we know that they're there, right? It just keeps going. Okay. Okay, so I hope you're getting a sense of this when we're solving an inequality versus an equality, and how we denote the solution set, particularly when we're looking at an inequality, right? So you're looking for the values of x that make the statement true. Okay, so I'm going back to Desmos with this example just one more time before we leave it. So Desmos will very easily show you the solutions to these things. So if we had h of x greater than g of x, and we just enter that in because we've defined h and g, right? Look what happens. It shades it for you, right? In fact, it even puts dashed lines at the values of those intersections, right? So where were our intersections at 20, 4800, and then down here at -5, 575. Okay, and so those intersections you noticed are along those dashed lines, and so it's highlighting the place where the graph of h of x is above the graph of g. Okay, so let's go the other way. The other one we had is less than or equal to. We have a less than or equal to sign in the keyboard there. There we go. Okay, so look what it did. Now all of a sudden those dashed lines are solid, right? Because we have less than or equal to. And it shaded the part where the orange graph is below the purple one, right? So it's for values of x less than -5 and also for values of x greater than 20, right? Okay, so I just want to highlight that. Desmos will do most things for you, but I'm glad that we talked about not only this quick trick, but also really looked at, where is the graph above and below, because that's really what's going on within an inequality. Okay.